Hello, welcome to another lesson of sectoral structures theory. Today we will continue on the last lesson of partial sums transformation, and we will take a few examples. The first thing I want to talk about is the relation between partial sums and isomorphic sectoral structures. So let AN and BM be two isomorphic sectoral structures. Then we propose that sigma bar is the partial sums transformation. Sigma bar of AN is isomorphic to sigma bar of BM. To prove this, we will write the sectoral structures in their partial weight form. So we will say let AN be the sectoral structure Wi, where I is 1 to lambda, where lambda is the order. We close brackets subscript n, where n is the degree. So this is our first sectoral structure using the weight or the partial weights format. And then we can say that BM is isomorphic to it. So BM, there is a number A which belongs to the natural numbers, or it can be a rational number, but for now let's say it belongs to n, such that BM is equal to AN times that natural number A. So when we want to write this in the partial weight format, we will say BM is equal to A times Wi, where I is equal to 1 to lambda, and then n, the degree, will become A times n. Now let's do the transformation, the sigma bar transformation. Sigma bar of AN is equal to Wi plus Wi plus 1 for all I equals 1 to I equals lambda minus 1. This is by definition. And we know that the degree becomes 2n minus the outer weight. And if you're unsure about some of these definitions, please review the prior lesson. Now let's apply the partial sums transformation to BM. This becomes AWI plus AWI plus 1 from I equals 1 to I equals lambda minus 1. And then the degree becomes 2AN minus A times the outer weight. Now let's factor A out of this equation. So this becomes A times Wi plus Wi plus 1 from 1 to lambda minus 1 times A. And then we also factor A out of this degree or the subscript here, and this becomes 2n minus the outer weight. And we notice that this is exactly equal to AN, sigma bar of AN. So this equals to A times sigma bar of AN, and therefore we can say that sigma bar of AN is also isomorphic to sigma bar of BM. So this is really useful to know because not all transformations maintain the isomorphism, but in this case it is maintained. Let's look at some more examples. Let xn equal to 3, 1 subscript 4. Find sigma bar squared of the conjugate of xn. So notice we have xn bar, so that's the conjugate of xn. And just a quick reminder, the conjugate of a sectoral structure is the resulting sectoral structure after we convert each alpha joint to a beta joint and each beta joint to an alpha joint. So by doing this for 3, 1 subscript 4, this gives us 2, 1 squared subscript 4, and you can do this manually, draw out the 3, 1 sectoral structure and convert the joints. Then the conjugate becomes 2, 1 squared subscript 4. Sigma bar of this is basically, let's expand it to 2, 1, 1. Sigma bar will be 2 plus 1 is 3, 1 plus 1 is 2, so it will be 3, 2 subscript 5. And because it's squared, we apply it again. So sigma bar squared of xn bar gives us 5 subscript 5, which is the theta 5 structure. So that's the final answer. Let yn equal to 4, 3, 3, 1 subscript 11. Let's find first sigma bar of yn, and that is pretty easy. So this gives us 7, 3, 4 subscript 17. Now let's find sigma bar of the involute of yn, and the involute, we basically draw a line of symmetry and we move the inner parts outside like this, and this gives us the involute of ym is 3, 4, 1, 3 subscript 11, and then sigma bar of that gives us 7, 5, 4 subscript 17. What we notice here in this case, the interior, or the center in this case, because it's just one, of the two transformations is different. However, we notice in this case that the outer parts, or the terminals of the sectoral structures are the same in this example after the transformation. Let's look at another example. Sigma bar of an is equal to 5, 3 subscript 8. We want to solve for an. So this is an example of a partial sums equation. There's many different types of those. This is our first example. So what do we know about an? We know that since the result after the transformation has an order of 2, then the order of an must be 1 degree higher, or 1 order higher. So 2 plus 1 is 3. So we can write an as being made up of 3 parts. What do we know about these different parts? We're going to write it as an equals to W1, W2, W3 subscript m, where W is the weight. We know that W1 plus W2 must equal 5. And we know that W2 plus W3 must equal 3. Now, when we're looking at natural numbers, there's only one possibility for 2 natural numbers to give us 3, and that is 2 plus 1. So W2 and W3 must be either, must be 2 and 1. Now, we don't know which is which, so we're going to try both. We will put 1 in as W3 in this example, and we will put 2 as W3 in the other example. And as such, the second part, or W2, will be the other possibility. And once we've solved for W2, then we have to determine W3 based on that. So for example, here we selected 2, 1, and because W1 W1 plus W2 must equal 5, then we know W1 is 3 in this case. And here it will be 1 plus something gives us 5, it will have to be 4. So really, we get two possible answers. So if we think about it, sigma in bar inverse of 538 gives us two possibilities, either 321 subscript 6 or 412 subscript 7. So two different sectoral structures of different degrees, both give us the same result after applying the sigma bar transformation. So this is our answer. Let's look at a harder one. Sigma bar squared of xn equals 85 subscript 13. We want to solve for xn. We know that the order of xn, lambda, in this case will be 4 because it's going to be 2 more than this one. So first let's solve for sigma bar of xn. We know it's going to be made up of 3 parts because sigma bar squared is made up of 2 parts. And we have two possible, and we have to solve. We will say W1 plus W2 will give us 8. And W2 plus W3 will give us 5. Therefore, we can say that W2 and W3 will be either 1 and 4, or we'll say 1 plus 4, or they will be 2 plus 3. And we can try to switch the order around. And based on that, we can also determine what W1 will be. So let's try this out. We will put 4, 3, so 4, 3, 2, 1 as possibilities for W3. And as such, this will determine W2. And then we know that W1 plus W2 is 8, so it's very easy to solve for W1. So this gives us 4 different sectoral structures. Now, we have 4 solutions so far, but we are looking for xn, not sigma bar of xn. So we have to apply one more step, and we're going to go from order 3 structures to order 4 structures. However, notice that every time you have a 1 in the structure, you can't go any further because there are no 2 natural numbers that you can add to get 1, where 0 doesn't count. So this first sectoral structure, 714 subscript 12, we cannot do a sigma bar inverse on it because it has a 1. So this is a dead end. We also have a 1 here, 441 subscript 9, so this is another dead end. So we are left with 2 sectoral structures that we could take further. So let's apply the same logic. Because we have 2's, it makes it very easy to solve. So once you see a 2, you know there has to be 1 and 1. So here we have a 2, so we know for sure there has to be 1 and 1 in the middle. And here we have a 2 at the end, so there has to be 1 and 1 at the end. And then we go in reverse. We have a 3 here, so 1 plus something must give us a 3, we know it's a 2. And 1 plus something must give us a 6, we know it's a 5. And we do the same here. And therefore we end up with only 2 sectoral structures as solutions for xn. 5 1 squared 2 subscript 9 and 3 2 1 squared subscript 7. So these are the solutions for this equation. Now, if the equation was sigma bar cubed of xn gives us 8513, then we would have to do the one more step on these. And because both of these contain 1's, that would be impossible. So therefore, if the equation was sigma bar cubed of xn, it would have no solutions in STN or in the group of sectoral structures, the set of sectoral structures. It might have solutions in later chapters, but so far it would have no solution. Thank you.